to 5 pi over 6, right? And so where's that? Between pi over 2 and 5 pi over 6, which is over here, like that. Then you wonder, is it just these 3 petals, or do we start, is that it, or is there more? How about here? We're going, the next one, 5 pi over 6 to where? 7 pi over 6, right? Where is 7 pi over 6 and where's 5 pi over 6? 5 pi over 6, it's not quite pi, so that's between here and, oh, we do get one in here, right? So, where was I? How does that go? Oh, wait a minute, wrong, but it's what? It's negative, so it's this one again, isn't it? So this is the red loop again. And if you continue on, you'll see that if we continue on, we don't get anything new. So cosine 3 theta is a 3-petaled thing. You might have guessed it would be 6-petaled, but it's a little funny the way things repeat or don't repeat. And the rules for even and odd numbers are a little bit different for sine and cosine. Play with it. You use some software. Look at it for yourself, okay? All right. But that's the method I use. I plot the polar graph and use that to then create the corresponding Cartesian graph. Yeah? Yeah, it's unfriendly. If someone asks you to find the Cartesian equation for this one, it's not nice. But I mean, I can do it. Here's a not so nice answer for that. I can say r is the x squared plus y squared equal to the cosine of 3 times the inverse tangent of y over x. Now this is good. This is okay for x greater than 0. See, inverse tangent only makes sense in quadrants 1 and 4, directly in terms of the angle. If you want to use inverse tangent to get angles in quadrants 2 and 3, you have to add pi, I think. Right. For example, if you wanted to find, check this out, guys. If you understand this example, you understand much. So this point right here is -1, -1, right? Suppose I want to find the standard polar coordinates of that. So r, square root of -1 squared, plus -1 squared, square root of 2, right? And then if you use theta equals to inverse tangent of y over x, that would give you -1 over -1, which would be inverse tangent of 1, which would give you pi over 4, right? And you'd be wrong, because that is not the standard angle at that point. What you've just found here are the polar coordinates of this point, right? This has theta equals to pi over 4, and r equals to root 2. So as you can see, inverse tangent of y over x fails outside of where it's, applicable, which is quadrants 1 and 2. This goes back to how we constructed inverse tangent as the local inverse between pi over 2 and minus pi over 2. So you have to understand that this pi over 4 is actually just this reference angle, right? So it's not theta, it's the reference angle. And then to get the actual polar coordinate there, you have to add pi, right? So if you look at the Wikipedia page on polar coordinates, for example, you'll find they've got this grand glorious formula for theta equal to. And on that, you'll find its inverse tangent of y over x. This is for x greater than 0. How's it go? Yeah, for x greater than 0. That's case 1, all right? And then they'll have its pi over 2 if x is equal to 0 and y is greater than 0. They'll have its minus 3 pi over 2. Or rather, it's 3 pi over 2 if x is equal to 0 but y is less than 0. And then finally, they'll have that it's pi plus the inverse tangent of y over x if x is less than 0. So technically, there's the case-wise defined formula for theta. You've got to be aware. These are the wrinkles that you face. I mean, it is what it is. Now, excuse me. We can combine ideas about parametrized curves and polar equations, right? Like we could use polar coordinates to parameterize curves, right? For example, this is kind of a new thing I'm introducing you guys here too. But if you wanted to parameterize the spiral, r is equal to theta, right? All right. Suppose you want to give the Cartesian parameterization of that. So in some sense, you know, in polar terms, you'd say this. You'd say r is equal to t and theta is equal to t. That would be a polar parameterization of this curve I'm talking about. What is the Cartesian parameterization? We'd say x equals to r cosine theta, y is equal to r sine theta. Basically, just use feed it the what we already did for polar. I mean, just use t cosine t and t sine t. This is a nice Cartesian parameterization of that spiral. It's kind of a neat, that's another direction we can investigate like that. So in view of that, if you wanted to calculate the slope, dy dx, for a curve, right? What did we say? If we wanted to do that in terms of theta, right? We can think about theta being a parameter, is one thing we can do. And if we think about theta being parameter, this is really dd theta of what? dd theta of y, of theta, right? Over dd theta of what? X of theta, right? And if y, and so we might say, well, that's dd theta of r sine theta, right? And over here, downstairs, we have dd theta of what? Of r cosine theta. So what's that give us? That gives us, well, it gives us dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. And so here, this is the slope of polar curve. R equals to r of theta. For example, we can find the slope of the spiral using this. For example, if we have r equals to theta has dy dx equal to what? So this one has dr d theta is 1, right? So it's sine theta plus theta cosine theta divided by cosine theta minus theta sine theta. So yeah, there's the slope on the polar spiral as a function of theta. It's kind of wacky. That will allow you to figure out where there are vertical tangents in your spiral, which is kind of neat. Just look for where the denominator is 0. What might make this more exciting would be to try something like this, right? If we try to feed this general idea, this line, what should it work out to? What should the slope of a line be? It should be 2. So what I'm proposing, and I'm not sure I actually want to do this, but if you were to, you could try differentiating r with respect to theta, multiplying it by sine theta, and then adding r cosine theta, and then dividing by this. And my claim is that if we're right, we plug that in, we should go to working out to 2. But I'm not going to do that, because I think I'm a little bit short on time for that. That seems like a 5-minute calculation to me. And I got 0 minutes, so there you go. Listen, tomorrow I will talk about how we use calculus to calculate area, polar areas. So basically what we'll talk about is if you've got something that's like this. So it's some area like this, you want to calculate the area of that. We'll describe that if this is theta 1, and this is theta 2, and this is r in, and this is r out. To calculate such an area, you just integrate 1/2 r out squared minus r in squared d theta from theta 1 to theta 2. I'll try to motivate why that's true and explain that. So this is calculating area with polar coordinates. It's new, it's a little bit different, but you already have all the tools you need to do it. Just another wrinkle. And we can also calculate arc length for like polar graphs. So we'll try to talk about that tomorrow. So, thanks guys. I did say we're having class tomorrow, right? Yeah, like it doesn't say otherwise in the syllabus, right? Okay. If it had said otherwise in the syllabus, I would hold to that, but otherwise we really should meet. So, all 3 of us, guessing, but yes.